Hi, I would like to thank the Muscat International Ophthalmology Conference and ISRS for this invitation to present on a new IOL power calculation formula named Pearl DGS. I cannot thank my colleagues Guillaume de Bellemanière and Alain Saad enough for their indispensable contribution to establishing this formula. We have no financial interest, and the access to the formula is free at iolsolver.com. This recent publication provides an open-source overview of all the details and key steps in IOL power computation with the Pearl DGS formula. This is the first time that the details of a modern formula have been disclosed, with the aim of sharing knowledge and contributing to improving that formula. The development of the formula was facilitated by the help of various partners, such as BVI Physiol and Canadian colleagues, and the previous work of famous pioneers in the field. The Pearl DGS formula is a so-called hybrid formula because it relies on an optical computational core but uses artificial intelligence for the prediction of the position of the IOL, which is considered as a thick lens, which makes it possible to take into account the design differences between the IOLs. Up to 6 predictive biometric parameters are used to predict the effective lens position, and the formula is compatible with all IOL models. And as we will see, it would work best if the design characteristics of the IOL are known. The ELP prediction itself is accomplished through the combination of several machine learning algorithms. Accurate ELP prediction is crucial because a millimeter deviation in predicted position induces an error of about 1.50 diopters with a 22 dioptric power lens considered as a thin lens. But for the same deviation of 1 millimeter, the error is 2.25 diopters for a 30 dioptric power IOL. However, the average thickness of an IOL being of the order of 1 millimeter, we understand that it is important to take into account the physical characteristics of the IOL. Indeed, for the same power, two IOLs positioned at the same anatomical distance from the cornea will, in reality, have a different power depending on the position of their principal planes. For the same thickness and a comparable position of the haptics with respect to the optics, two IOLs of different design must occupy identical positions but can have a different optical effect even if their labeled power is the same. To make this even more complex, the position of these planes varies for the same model depending on the power of the IOL. The Pearl DGS formula is optimized to best manage this type of problem. We first establish the formulas that allow the position of the optical planes of a thick IOL to be back calculated from the pre-op biometric data, the postoperative outcomes, and the design characteristics of the IOLs. If we know the position of the theoretical planes and the design of the IOL, we can calculate the anatomical position of this IOL. So, for each eye in a large training set made of well-documented eyes operated with a fine vision IOL, we could back calculate the optical position of each IOL and could then deduce the anatomical distance from the corneal endothelium. This was possible because the manufacturer provided us with the optical design of each IOL for all the powers available. An algorithm was then trained to predict these positions. This algorithm is now used in the formula to predict the optical and the anatomical position of the IOL to be placed. Since the anatomical position of the IOL is predicted, it is possible to optimize the Pearl formula for any type of IOL if its design characteristics are known. In the meantime, the formula uses the constant A to optimize its result for different types of implants. In optical biometry, peaks are obtained when light takes an identical time and not an identical physical distance between 2 points. An empirical fix was published by Dr. Cook to modify the actual length, and it is used in the Pearl formula. When the posterior corneal radius is known, it is possible to enter this information in the formula. However, if the posterior corneal radius is not measured, An algorithm designed on a preliminary study makes it possible to predict the value of the posterior radius thanks to a regression formula, so as to obtain a more precise value than with the approximation based on the keratometric index and the anterior radius of the cornea. This slide shows results for the Pearl as well as other formulas that have been compared for accuracy in various recently published independent studies. In green are the median of the absolute error value for which the formulas were the best, and in blue those where they were in second position. We encourage you to use this new formula, which also presents exciting options for eyes with refractive surgery, as well as to take advantage of the results obtained for a patient's first eye. This is the second eye option. A recent study confirms the validity of this approach. Thank you for your kind attention.